Assalamualaikum warahmatullahi ta'ala wabarakatuh. Good day everyone. For today's lecture, we will cover chapter 2, which is transition temperature. In this chapter, the subtopic is about the thermal property of polymer, states of matter or viscoelastic behavior, first and second order transition. So in this chapter, we take up the subject of the glass transition, whereby a polymer liquid is cooled in such a way as to solidify without adopting a crystalline packing. So as we all know, all polymer can form a gaseous state, but not all polymer can form a network crosslink. Okay, network or crosslink means that a significant fraction can never crystallize, but all polymer can form a gases. To begin with, we need a working definition of a glass. What is a glass? So a glass is actually an amorphous solid. By amorphous, we mean that there is no long range order or symmetry in the packing of the molecule. So the word symmetry is related to the crystalline structure. So in amorphous, there is no long range order or symmetry, means that it is not in a order structure. Okay, in this sense, the structure of a glass look very much like the structure of a liquid. However, a glass is a solid, so it does not flow over relevant time scale. Although the preceding statement is apparently innocent, we use a relevant time scale hints at a fundamental complexity. For example, when a polymer liquid is cool, so of course the density of that polymer will increase, and what we call the molecular relaxation time is increased, means that the level of the molecule in that structure is in a relaxed time. Okay, it is in calm time. So over some range of the temperature, the molecular motion will become so slow that an equilibrium packing of the molecule cannot be attained during the experiment. So when this happens, we can say that the sample has undergone the glass transition, and we associate with each polymer a glass transition temperature, or the Tg. And the value of Tg is the single most important characteristic in choosing a polymer for a given application. And it must lie significantly above any temperature at which we intend to use the polymer as a solid, but below any temperature at which we intend to process the polymer as a liquid. So as we will see in practice, Tg is not thermodynamic property of the polymer, and it can adapt a range of value for a given polymer, but nevertheless, it is an extremely useful parameter. Okay, faham tak? Now we continue with the melting temperature. But before that, as I mentioned earlier, many polymers cannot crystallize, so they exist in an amorphous state. And for a polymer that can be crystallized, we can measure its melting temperature, and we call it as a semi-crystalline polymer. The crystallization of the polymer is actually a very complex process because the long chain must arrange themselves into a defined crystalline structure. Because the intertwining of the polymer, or we call it as the entanglements, are an obstacle to crystallization, this is a relatively slow process. And additionally, crystallization of the polymer is usually imperfect and will lead to the creation of a partially crystalline, or we call it as a semi-crystalline material, in which both amorphous and crystalline domains coexist. And we can measure the amorphous and the crystalline area by using X-ray spectroscopy, and we can know the the amorphous phases where the crystalline phases appears as peak in an X-ray diffractogram. We can use the X-ray, what we call X-ray diffractogram or X-ray diffraction. An analysis of the phase transition upon heating a sample also provide valuable information about whether a sample is an amorphous or crystalline. And the morphology of a solid greatly influence the properties. For example, the optical, the mechanical, and also the thermal properties of product made from polymer. Amorphous and crystalline solid, it can be differentiated by their thermal phase transition. When the crystalline substance are heated, a melting point is observed in analogy familiar from low molar mass crystal, and at the melting point, also known as TM, an abrupt rearrangement occurs in the material. Below the melting point, which is below the TM, there is a crystalline order and this disappears during the melting process. This is the reason why the properties such as the volume undergo a stepwise change at the melting point. So thermal transition is actually the first order phase transition. So we can measure the enthalpy, which is the enthalpy of the melting. And because of the structural changing on the melting, the entropy of the melted phase is greater than that of the crystalline phase. So we can have a delta S, which is transition, can be defined for this transition, as well as a corresponding free enthalpy. Free enthalpy is given by delta G. Also use differential scattering calorimetry or DSC to examine the percentage of the crystallinity of the polymer. Okay, by the way, now we proceed. Polymer can be characterized by a melting temperature Tm and a glass transition temperature or Tg. Tm is the melting temperature of the crystalline domains of a polymer. So Tm is related to the crystalline domain and Tg is related to the amorphous domain. And the amorphous domains of polymer take on the characteristic properties such as brittleness, stiffness, and rigidity. Now we look at the thermal property of the polymer. Completely amorphous polymer, we can determine the glass transition temperature. For completely crystalline, we can determine the Tm or melting point. And semi-crystalline, it will have both Tg and Tm. Okay, as we can see, the crystalline region is in the order structure, while the amorphous region is in a coiled random structure. This one shows the table for the Tg and Tm of the some polymer. For example, we have polypropylene. It has a Tg of -10 and Tm of 175. It is considered as semi-crystalline polymer. And for amorphous polymer, for example, polystyrene, it has a Tg as high as 100 degrees C and it has no true melting point and it gradually softens until it melts. Okay, this one is the schematic diagram represent the glass transition, the crystallization, Tc, and the melting temperature, which is Tm. Okay, Tg right here, the point for Tg value is in the middle of the decline here. Okay, dekat tengah-tengah ni, point Tg. So above Tg, which is above Tg, here, right here, the cross-linked amorphous polymer exhibit a rubber elasticity. Example is styrene butadiene rubber (SBR), which is widely used in the materials ranging from rubber band to the automotive tire. And polymer that cannot crystallize usually have some irregularity in their structure. So example include the atactic vinyl polymer and also the statistical copolymer. Basically, at low temperature, amorphous polymers are glassy, hard, and brittle, and as the temperature is raised, they go through the glass-rubber transition, and the glass transition temperature is defined as the temperature at which the polymer softens because of the onset of the long coordinated molecular motion. With the crystallization, the development of the crystallinity in polymer it depends on the regularity of structure in the polymer. So basically, the isotactic and syntactic polymers will usually crystallize, whereas the tactic polymer, with a few exceptions where the side group are small or highly polar, do not. So a tactic polymer basically will be an amorphous polymer. And basically, non-regularity of structure, which is the amorphous polymer, it will non-regularity of structure first will decrease the melting temperature and finally prevent the crystallinity. That's why in amorphous polymer it does not have the exact Tm value. If we have a blend of isotactic and atactic polymer, okay, kita campur isotactic dengan atactic, it will show a reduce in the crystallinity, with only the isotactic portion will be crystallized. And under the some circumstances, block copolymer containing a crystallized block will crystallize. Again, only the crystallizable block will crystallize. And the factors that control the melting temperature include the polarity, hydrogen bond, as well as the packing capability. And Tc is actually the crystallization temperature at which the temperature, the polymer show the temperature at which it form a crystallized region. For Tm, it is the point of the polymer melt. And when a crystalline polymer is melted, the melt is actually an amorphous region. So above the melting temperature or melting point, crystal melts and polymer will flow. And on melting, the sample will become clear or more transparent. And crystalline polymer are stiffer, stronger, harder than the amorphous polymer. For Tg, above Tg, polymer are soft, rubbery, and flexible, but below Tg, polymer are hard and rigid glass. This table illustrates the mechanical or thermal properties of an amorphous polymer. We have PC that have the temperature used. Okay, temperature used in range. For example, we have polycarbonate temperature use of -40 to 120, and the tensile strength of 65 to 70. And many factors contribute to determine the tensile strength of amorphous region. For example, the side group, the side chain, the chain length will affect the temperature and also the properties, including the mechanical and physical properties of the polymer. Now we proceed with the slide. Temperature state for application of amorphous thermoplastic resin is known as the glass condition below the glass transition temperature. And the molecular structure is frozen in a definite shape, and the mechanical properties are barely flexible and brittle. Figures show the temperature behavior of an amorphous thermoplastic resin. So the glass transition temperature, or Tg, of an amorphous or an amorphous crystalline material is the temperature at which it changes from a brittle or vitreous state to a plastic state. Below the Tg level, polymer become hard, plastic,